this is Organic Chemistry 9, the final part where we talk about intermolecular forces in organic chemistry. What do we mean? Let's just recap on that story, shall we? Remember we said that we can get a C and a C forming together and the H's come around so that we eventually end up, let me just make a, oops, okay, let me get this back to, okay, just get this back to black, okay. So we said we had a carbon which linked up with a carbon, I don't know, let's link it up with, let's link it at this stage like that. So that is a, okay, not an A, it's an H. A, I'm thinking alkane or alkene. H, H, and H. What have we got? It's an ane, and it's ethane. Now, methane, ethane, propane, butane, hexane, blah, blah, blah. Pentane, hexane. Now, essentially, we have got a bond over here, right? These are all our bonds internally. Can you see? I'm highlighting those. Those are intramolecular bonds. And we said that this atom, this molecule over here, as we've got it, it's basically covered in hydrogens. So this thing on its own is non-polar, right? Now the next step is we're going to say, but there's one molecule of ethane. How does that molecule of ethane link to another molecule of ethane? C, C, H, 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 okay? We're now going to be looking at the forces that bond these two together. All right? How do we do? This is intermolecular forces, bonds, okay? Now we also remember intermolecular forces, intermolecular bonds. So when we've got these two molecules together, we are actually looking to see how strong are those bonds. Why? Because we need to know a little bit about this. Depending upon how strong they are, it means that this one, and let me get another one out here. Let's pretend this is our ethane, and there's another ethane. We want to know how strongly these guys are bonded together, because that will tell us about the properties. It will tell us how easy it is to split these apart. And when we split them apart, what are we doing? Essentially, that is the boiling point. Okay? Let's just take that at this point. Remember with water, what did we do? We put enough energy in to convert a water molecule from a liquid to a gas. Remember? Okay, here we go. Here's our liquid, H2O, and we had our little guy there. And when it boiled, right, we gave it enough energy to fly. In other words, it's moving, so its EK was a half mv squared. Now that's important because the mass comes into it. Obviously, first of all, we have to break the intermolecular bond between these. Then they're going to go faster and faster until we can fly this away. So the strength between the bonds is enough, or it's information that tells us basically what the boiling point with this would be. Now, that tells us about the physical properties. It tells us, gives us indications of whether it's a liquid or a gas at room temperature, doesn't it? If the boiling point is -5 degrees, it means that at -5 degrees, let's say Kelvin or centigrade, it doesn't matter for our discussion, it means that it's a liquid. Remember the phase diagram that we had previously? Okay, there is a liquid, there's a gas and there's a solid, remember? And, okay, over there is the boiling point where you've changed it to a gas. Correct? Okay, there she is. Okay, now, when we're doing this, we have to keep in mind two things. There's the forces acting together, like so, and there's also the mass of this thing. Because the energy, remember, energy and temperature are together. The energy to make this fly is actually the energy. It's the velocity. So the heavier it is, the more energy we need to make it fly. Try throwing a brick versus a tennis ball. It's quite as simple as that. Okay? I'm just going to leave these guys here for a moment because we're going to refer back to them a few times. So let's just have a look at intermolecular forces. Allow me to recap. Okay, let me just recap this. Whoops, Kevin. Let's recap intermolecular forces. Right, we had ionic. And what did we look at? We looked at difference in electronegativity greater than 2.1. As I said at the time, please remember different textbooks may have different numbers, okay? I have seen 1.7, 1.9, 2.1. The concept is what we're after here. You'll be working in your own parameters, but the concept is what's important, or the parameters that you are given from your specific textbooks. Now, what we're saying is if the difference in electronegativity is greater than 2.1, it is an ionic bond. Remembering that an ionic bond has a positive ion and a negative ion, because an electron has gone across to there making it negative. The electron is, let me say, captured over there. All right? It never goes back to the other side. So this is a totally, the electron has gone from the one to the other. That's an ionic bond. Okay? Sodium chloride and magnesium sulfate, calcium carbonates, all of those become ionic bonds. Now, the next side is to look at a hydrogen bond. In a hydrogen bond, I'm going to use water specifically. Remember, we said that this was negative, this was positive. The little delta sign means partially. Okay. For those of you who do maths next year, you're going to come across him in maths as well. Partial things. Okay, so what we've got there, it's partially. It means that the electron spends a lot of time on the oxygen, but it's not totally all the time. It's not an ionic. Then what happened was we had the hydrogen bond coming in over here, delta minus, delta plus, and we had that guy forming over here. This was the hydrogen bond. Okay. We had a graph, if you like, of boiling points of ionic, okay, polar, dipole, dipoles, right the way down to the weakest ones, which are London or dispersion. We had those, and we saw water and ammonia, and then it went down and went up like that, right? So essentially, we're going to come across a similar graph, not that it does that kind of funny shape, but a similar graph. Now, I better just move these because they're probably going to go flying as I move this away. So that's a hydrogen bond, all right? Now the next one that I'm going to do is a dipole-dipole. Dipole, dipole. Remember, that was A and B. This side was positive. This side, doesn't matter which is which. This will be attracted to either A and B, or it could even be a C and a D. Anything with a negative and a positive side. This is a dipole. Dipole, it must have a north and a south, is a dipole magnet, and it must have a a plus and a minus side for a molecule. It can't just be a plus. It has to be a dipole, two poles. So now we've got that, and then we have a bond forming between these guys, like that, or we have one forming. Remember, I just drew an AB if they were the same, but it could be linked to something with a C and a D atom sitting inside there as well. And as long as I've got a minus and a minus, this is a dipole and this is a dipole here, like that. Okie dokie. Now we're moving up over here, and the next set that we're going to do is the London or dispersion. London or dispersion. Okay. These are basically weak and nonpolar. Okay. They're weak and they're nonpolar. All right. Intermolecular forces. I'm now going to draw a line down, and that line is going to be in red, and it's going to be from strong, okay, strong there, all the way down, and let's go up a bit to here where we've got weak. And this is the bond, I'm going to say intermolecular bond strength. Right? The intermolecular, ionic strong, hydrogen, dipole, London dispersion. Okay? Therefore, if something is held together by a hydrogen bond, you're going to need more energy to break those bonds and make it fly, so to speak. Now, let's have a look. How does alkanes, alkenes, and alkynes? Let me summarize. So, 1, I'm going to look at alkanes, alkenes, alkynes. Whoops, like so. All right, the standard ones. Let's just take a simple one like so, and you could even have a like so. Okay, I haven't put the hydrogens in. If you want me to, I will. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 4, and we've got that. Okay, now obviously there's hydrogens all around there, right? I'm not going to bore you with drawing hydrogens. Alkane, alkene, this is our ane, this is our ene, oops, ene, and this one is our ine. What am I now going to do? Now I'm going to look at how does an alkane molecule, how do these alkane bond to another alkane? Oops, sorry, alkane like that. How do we do similarly for the enes and the ines, okay? And the ines. I'm not going to do each and every one, but they are similar. So I'm going to just take a simple one like this. C, 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 and it goes on like that, right? There we go. And maybe it could be longer like that. Now, the next one is the same element. So it's meth-eth-propane. So another one, meth-eth-propane, right, comes and sits on top. First of all, this, as it is, has got hydrogens, and remember, it's nonpolar. Why? Because there's no place for a second, I'm just going to leave it as that, a second pole. Okay, these are hydrogens over here. So let's say they're all pluses. Okay, they're all pluses there. Therefore, there's no place for a second pole, right? There isn't a negative bit. Okay, this is the concept that we need to get through into our minds, that an alkane, now if you think an alkene is the same, and an alkyne is also pretty much the same. We don't have a place for a second pole. So therefore we say these all form nonpolar bonds. On an intermolecular basis. Therefore, every one of those is a nonpolar. All right? The next thing we have to think of is this. Let's say I've got these two carbons like that. Okay, here we go. Okay, I'm going to just pull out. Unfortunately, I wished I could handle more than two at a time, but I'm afraid we can't. Okay, this is where you need one of your assistants from the audience, isn't it? Let's look here. Here we go. Okay, here's ethane, ethane, ethene, all right, or even ethyne. They're sitting on top of each other. This is nonpolar, so they are held together by London forces. So the intermolecular force is London or dispersion, which is weak. So the bonding together of these two is actually very weak, which means that if they are weak, their boiling point is low. Okay, it's all relative. Okay, it's low. So there we go, and we've got another C and a C, and they are linked over here. Da-da. Okay? Okay? Just conceptually, they're linked like that. Okay, so let's say, argument's sake, we're not putting numbers, okay? The force there is 1 and another 1, so the total force is 2. Okay? So far, so good. What if we have now, and this guy, 1, 2, 3, 4, 5. So here we've got pentane. Okay, we've got here more carbon atoms. Okay, so first of all, we know that it's heavier. Okay, heavier means more energy to convert to a gas. On its own, it's heavier. Now, okay, I've only got 4. But what are we saying? We're saying that therefore, but here, the force to break one molecule of pentane apart is 1, 2, 3, 4, is 5. So the longer the chain, the bigger the force. It's like a zip, okay? Think about it like that, all right? Think about it like that, okay? Think about a zip. The more sides you've got, the more teeth you've got hooking, the more reliable or the greater the bond of the zip, isn't it? So the longer the chain of carbon atoms, the more of the London forces, which means to tear it apart, to actually boil it, you need more, and it's heavier, so you need more there as well. So that's pretty straightforward. Our next portion, okay, is going to be intermolecular. The force increases, we've done that, okay, and it is also, just to finish it off, all right, okay, it is spread over a large surface area. Well, that's pretty obvious, isn't it? Look, there's 4 of the tennis balls, now there's 2. I've doubled the surface area, I've halved it and I've doubled it now, haven't I? That's pretty straightforward. And the zip tells you the same story. When you think of it, just have a look at a zip. A short zip versus a long zip. Okay, try and pull the long one apart. Much, much more. Piece of Velcro or Velcro. Hey? Or Velcro. There's another good one. Okay, a short piece of Velcro and a long piece. I mean, try and pull that apart like this. You have to tear it apart like that, don't you? Okay, so the longer the chain, the greater the London force, therefore the higher the boiling point. The same is for the alkane, alkene, and alkyne. Okay. Now, also, we need to know that some haloalkanes, let's have a look at haloalkanes. All right, I want to get my numbers right here. That was number 1, alkanes, alkenes, alkyne. Haloalkane, let's call that number 2, shall we? Now, when we're looking at this, I want you to say to yourself, okay, haloalkane. Now remember, they also can be longer chains, correct? The same is going to apply on that. But some, okay, most haloalkanes are non-polar. Why? Let's have a look and just give ourselves an idea. I'm going to put in over here, all right, let me just complete. I'm going to put in over there, this is an al, not an al, this is a halide. The difference, this is a halide. So I can put fluorine, chlorine, let's take them down, bromine and iodine. Okay, they are ions that go on, are they not? Remember, they're ions that go on, halogenation, hydrohalogenation, or come off, dehalogenation, dehydrohalogenation. So we've got a halide on there. Now what we're saying is they are, most of them are nonpolar. How did we work it out? We took the delta electronegativity, didn't we? Okay. Let's just look at it. Let's have a look. Here's the carbon, and here's, for example, iodine. Okay, I did a few here. Carbon and iodine is 2.5, 2.5. Delta electronegativity is 0. Well, let's make a table, shall we? All right, carbon, iodine, and delta, whoops. Okay, I haven't done this table in my notes, but let's just do it over here. Carbon is 2.5, 2.5. Delta electronegativity 0. Therefore, non-polar. Can't be. Let's move up to now to bromine. Carbon, bromine. Carbon 2.5. Bromine, bromine 2.8. Remember, you always put the most electronegative first, so it's 2.8 minus 2.5, 0.3, non-polar, or very, very, very weakly polar, right? Carbon iodine next. Sorry, not iodine, carbon chlorine next. All right, so we got chlorine next, and that's going to be 2.5. Chlorine is going to be 3. So my delta electronegativity is going to be 0.5. Now you can start seeing that this is starting to become polar. Okay, it's weak, but it has a polar possibility. What about carbon and fluoride? Fluorine, okay, fluoride in this case. Okay, so we'll say that's 4, 2.5, 1.5, polar. Okay, the fluorine end of that is going to be negative, and the other is going to be positive. So this one is more than likely going to be the dipole. Okay, there we go. That is why they say most haloalkanes are nonpolar. Moving along to the next section, we've got, I'm going to look at, next is a dipole-dipole. Dipole-dipole. These are ones that we don't look at very often. Aldehyde and ketone. Aldehyde has got a CC with a double bond O at the end, correct? That is its trademark. What that means is if it's an O, it's negative. Remember, a ketone has a double bond O in the middle. So the smallest ketone has 3 carbon atoms joined to it. There's a reason I'm saying it, because on the graph, when we look at the boiling points, you will see that the ketone starts at 3 carbons because you cannot get it. It's the same as an alkene. I can't get it with 1. I can have to get it with 2. So we'll see that when we look at the graph. Okay, we don't generally get that situation. Okay, that's going to be positive over there, and the other side of that's obviously going to be the positive on the carbon side. So we're heading for, these are going to be dipole dipoles. So we would be able to get a bond with that when we have 2 ketones or aldehydes. All right, the intermolecular is going to be dipole dipole. So in essence, if we're now plotting, we've got the alkynes, alkenes, alkanes underneath with their halo counterparts, except possibly for one with a fluorine. We've then got above it, you've got the aldehydes and the ketones. The next step above it is we're going to look at the hydrogen bonds that occur. Hydrogen bonds, right? Hydrogen bonds. And there are 2 that we study that have got hydrogen bonds. What will they be? The first one is an alcohol. You go, ooh, let's just have a quick look at this alcohol, just a simple character over here. We draw it like that, don't we? With our H's around there. Remember, I spoke before in one of the sessions that we did, I'll just bring that down a bit. We said this piece here is actually like that. Okay, an O, and we've got to conceptualize that there's an H on the end of that. The way we conceptualize this is we say, all right, we have our alcohol over here with an O, and we stick an H down there, just to give us an indication that that's an OH, but the O and the H is bonded, because the O and the C are bonded in electron-electron, and there is like that, and O is -2. So there's the 2 electrons that come with the O. Correct? Yep. Now what happens is the next, this is ethanol, okay, maybe a Shiraz or a Chardonnay or whatever you will like. That there is an alcohol. Now how does the next one join to form this glass of whatever wine it is? Simple. We have a hydrogen bond over here. All right, this guy is plus and this guy is a minus. So what do? I now come along and I put another, okay, another one comes on here with a hydrogen, okay, which is a plus, an O, and a CC, like that. And we have the hydrogen bond forming over there between those, over here. Now can you see over here we have 1 hydrogen bond. It's important to see that. What happens here with this hydrogen is this hydrogen down here, I'll just continue it. It may be in red. This, no, change color, Kevin. Let's put in another one. This hydrogen down here is going to link to another H, isn't it? Like that. That is another negative. So this is another hydrogen, but that's a separate bond. The 2 are linked together like that. 1 hydrogen bond to that one. What about the next level up? The last level up that we studied was the carboxylic acids. Remember, these were the oic acids, right? Methanoic, ethanoic, hexanoic, and all of those, and we use them with alcohols to get esters, etc., etc. So here we go. Let's look at meth-eth-prop. Okay, let's look at propanol, just to be different. Propanol has got an O and an H, an OH. I'm not propanol. It's not what I want to. Propanoic acid. Right, propanoic acid. I'm just going to look at there. Meth-eth-prop. And I have to put my double bond O on top. Now I know the O is negative. I know that's positive. And I know that's a negative side there. So what happens now? Now along comes another. Okay. This is one. Okay. One molecule of meth-eth-propanoic acid. Right? One molecule of propanoic. Now along comes another one. What color did I draw it in last time? I did also kept it in black. Along comes another one. Now a hydrogen sits up there. Okay, I've just got to get myself down over here. An O plus, and coming down over here is it's my OH over here to a C. And over here is my double bond O, which is negative, to a C. Okay, like that. Along comes, look here. What do we have? We've got a hydrogen bond and a hydrogen bond. So each carboxylic acid, acid has two hydrogen bonds. Therefore, the graph that you'll see, and most textbooks have got it, I'm just going to draw it simplistically over here. All right, please, we are looking at a concept here. I'm not putting numbers. Okay, that's the middle. That's plus degrees. Oops. Okay, this is temperature here. This is number of C atoms. 0, okay, 1, 2, 3, 4, 5, 6, 7, 8, and so on. All right. So what we're saying is that this is below, okay, 0, and we'll put it in C. This is above 0 degrees Celsius, okay? So this is a minus temperature, and that's a plus. What we find, and I'm going to see if I've got enough colors, otherwise 1, 2, 3, no, I don't. But anyway, I'll start off with black. So at the bottom, right down here, okay, I have actually got the alkenes. This is the alkene. Just above him, I have got the alkanes. Okay. This is the temperatures, okay? The boiling point. Let me put that in clearly. Temperature, this is the boiling point. Okay, we are plotting the boiling point of this. Okay, I'm going to go this one, there, 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 there. Okay, you can get the gist of it. And the blue boiling points, oops, sorry, the blue ones, okay, one atom. Okay, that was an alkene. I have to start at 2. An alkane, I can start at 1. Okay, so my alkanes, okay, my alkenes at the bottom, alkanes just above. Okay, that's an alkane. Okay, alkene, alkanes are just above, because the alkane is actually a stronger London force bond than the alkene. The alkyne's just around the same sort of level. The next one up, we said, was going to be, that we looked at, was going to be the aldehydes and the ketones. The aldehydes and the ketones are also fairly similar to each other. Okay? aldehydes and ketones. Aldehydes and ketones, the aldehyde slightly underneath, green. The aldehydes, okay. Remember, you can have an aldehyde with 1, 2, 3, 4, 5, 6, okay, 7. Okay, so I can have that there, which is the aldehyde. Like so is the aldehydes. The next one up is going to be the ketones, and they are very similar. I'm just going to put the ketones in like this. Whoa, there's an error there. Okay, I wasn't thinking. My ketone has to start there only. Right? My ketone starts there only because I cannot have a ketone with less than number of carbon atoms 3. 1, 2, 3, 4, 5, 6, 7, 8, etc. This is the smallest ketone because it must go in the middle. Okay, there's got to be 3 carbons to have him. Lastly, or the last 2, is the alcohol, and then the acids. Okay, I'm going to go for red for the alcohol. All right, red, I'm going to go a solid dot. So red, okay, I've got here up there, let's say there, 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 there. I think you sort of get the gist of what is happening here. Okay, the alcohols are doing this. Oh, the green one was the ketone. The red one is the alcohol. And the last one on top, I'll go back to the black, and I'll call that one is going to be the acids. And we're up here now. 1, 2, 3. Okay, I'm just trying to give you these are the, okay, move it down. Carboxylic acids. That shows us that as the number of carbon atoms increase in the chain, the boiling points go up. So on its own, the boiling points go up of the alkanes, of all the groups. Right? Why? Because the length of the bond is more, and it's also heavier. But every time that we go, if we look at, let's take a 4-bonded one. A 4-carbon atom alkene-alkane is low. A 4-bonded, I'm over here. I'm just going to put in, no, not erase. I want to put in a thing. I'm looking here. Okay. I'm going up the chart. The alkene-alkanes are the lowest. They've got 4 carbons, but they're London forces between them, which are low. However, you need energy because it's heavy, and you've got 4 of them to take apart. The next one's up, okay, the aldehydes and the ketones, they have got dipole-dipole forces. So although there's 4, yeah, there's 4 of them, there's dipole forces between the next 4 on top, which makes them stronger bonds. The next 4 up is going to be the alcohol and the carboxylic acids. The alcohol, 4 of these together, meth, eth, prop, butanol, with another butanol on top. Okay, the bonds between them are single hydrogen. Then you go the next step up, and you're going into the carboxylic acids, the OX, and over there we've got meth, eth, prop, butanoic acid. It's linked to the next butanoic acid molecule via a double hydrogen bond, so its boiling point is higher. So although they've all got 4 carbons, their intermolecular forces are different, holding them together. Thanks for watching that. That brings us to the end of the section on organic. My bad, I have gone over on this, but I kind of couldn't stop it in between, so my apologies. Thanks for watching, and we'll continue with the next section, which is equilibrium chemistry, rates of reactions. Cheers, bye.